Hello, hello, how are you? It's look you're fine, looking fine. Are you fine? Is it okay? Yeah. Let us start the discussion. Now we will start the general session on atomic theory. That is regarding some keywords and all. I will discuss atomic theory. Okay. Okay. Everything in the universe can be divided into forces and particles. Okay, they are classified in such a way that gravity, magnetic separation, magnetism, strong internuclear forces, that I will come back to that one. I will do it for that. Yeah. So let us see. These are forces and particles are separated in such a way: gravity, magnetism, strong nuclear forces, weak nuclear forces. And other particles are matter, antimatter. Okay. Now if you see this forces acts on all matter, gravity acts on all matter. Okay. Antimatter that all pulls or pushes, magnetism. Strong and weak nuclear forces hold the nucleus together, like this here showing here. Okay, here I'll come back to it in a while. That can be divided. Yeah, that is better than this one. Now you can see this is discussion we're doing gravity and magnetism. Actually, gravity on all matter, that magnetism acts on charged particles, so it will always pulls. Oh, that is gravity. Magnetism pulls or pushes, that is magnetism. Strong or weak nuclear forces hold the nucleus actually together. in this discussion. That means forces are of two types: gravity and magnetism. Gravity acts on all matter and always pulls. Magnetism acts on charged particles, pulls or pushes. Right? Next, forces. Magnetism is about 10 power 40 times more powerful than gravity. See, 10 power 40 times means how many zeros we wrote. So magnetism is always 10 power 40 times more powerful than gravity. So now particles are divided into matter and antimatter. Matter and antimatter. Here, that is example, we have electron and proton. Is electron and proton. You can observe here, electron is a matter and positron is antimatter. And the picture below shows three objects that can be classified in the same group. Which of the following statements is true for all these three of these objects? So they are metals, they rust, the metals, they rust rapidly, they weigh the same, they are the same color. Okay, so they are the same color is a picture which gives an idea, right? The picture is now showing idea about the object. Okay, so nice discussion that is happening here. Hope you're all enjoying. And in this, we have metals are there, they rust rapidly and they weigh the same, they are the same color. Now we will see which pair of elements is most similar. Which pair of elements is most similar? First one we have calcium and fluorine is there. The next we have sodium and chlorine are there. Next we have neon and argon. Then we have lithium and hydrogen. Lithium and hydrogen are there. Okay, so here we are observing the things related. That means calcium, fluorine, sodium, chlorine, neon, argon, lithium, hydrogen. The most similar cases are there. So if you take copper as an element that is used in electrical wires, what is the smallest unit of copper that still maintains the characteristics of copper? Hence the characteristics of copper. So maybe atoms, electron, the nucleus, or the proton. So copper is an element. Copper is an element. Copper contains atoms. Element contains atoms, contains electrons, neutrons, nucleus, and proton. Now, in making a pizza, which process involves in chemical change? So, mixing spices for the sauce, slicing pepperoni for the topping, spreading cheese on the pizza, baking the dough to form the crust. These are the different examples to be studied. Now, what is the smallest particle of the element gold that can still be classified as gold? Is it an atom? Is this molecule? Is it neutron? Is it proton? We'll see. These questions can be answered only when we know the backup about the atomic theories. Now, which of the following illustrations represent a pure substance? See here how the elements are there. Looks different pictures we have. Suppose if 1 kilogram of a compound toluene melts at minus 95 degrees Celsius, then 500 grams of toluene will melt. So it indicates melt at minus 47.5 degrees, 95 degrees, boils at 95 degrees, boil at this one. So this amount, half of the amount taken. Next, the drawing below represents a bit used in a power drill. Which of the following metals is most suitable for making this drill bit? Aluminium, copper, gold, steel. Okay. Which statement about the molecules in ice and the molecules in liquid water is correct? The molecules in ice have more energy than the molecules in liquid water. Molecules in ice contain different atoms than molecules in liquid water. Molecules in ice have more electric charge than the molecules in liquid water. And the molecules in ice are less free to move than molecules in liquid water. So this type of things can be studied after knowing the atomic theories. Which formulas represent compounds? O2, H2O2, CO2, H2O, H2CO2, H2CO2. Like they see in this, compounds are mixtures of elements. In this, H2O2 is a compound, O2 is an element, while that of CO2 and H2O are compounds. So these are the compounds who we can understand that CO2 and water are compounds. Which is an example of a chemical change? Pepper being ground into a salad, a match being lit, sugar being dissolved in water, wood being chopped. So these are the 4 different things. Chemical change means the chemical pepper being ground into salad, match being lit, sugar being dissolved in water, wood being chopped. See different questions to understand before starting the atomic theory. Which statement is correct concerning the mass of a ball of clay? Mass changes as the altitude of ball of clay changes. Mass changes as the shape of the ball of clay changes. Mass of the ball of clay is unchanged by altitude or shape. Mass is doubled when the ball of clay is divided into two equal pieces. So, different things like, see, if different kinds of atoms are represented by different colored dots, which picture represents a sample of compound? Here also you have confusion. That means same things are there, they are elements. Different things are there, combination, there is compound. Then go with the second one. Which of the following is a compound? Oxygen, water, nitrogen, air. See, water is a compound. Air is a mixture of compounds. Evidence of a chemical change would be melting popsicle, spinning top, spilled bucket of water, rusting car fender. So, rusting. Which symbol represents carbon? Ca, N, K, and C. It's C. Moisture that collects on the outside of the cold glass results from the process of evaporation, condensation, sublimation, vaporization. So outside, which is nothing but condensation. Next. So particles may be matter and antimatter. In that, proton is an example of matter. Let us see what is matter. Matter is different types, quarks and leptons. Quarks, we have fractions up 2 by 3, down minus 1 by 3. Leptons, electrons, Fermi-lab. Electron, world's highest energy particle accelerator. 4 miles in circumference, particles go around 99.99% of the speed of light. We send protons and antiprotons in opposite directions and smash them together. That is what happening in this discussion. Particle accelerators. Particle accelerators. Picture showing here. That is the particle accelerates. Proton made of 3 quarks, 1 up, 2 down. Yes. Neutron, 3 quarks, 2 up, 1 down. Can we see atoms? Yes. Magnesium atoms are white. Above are there, they are present. Boron atoms are gray, seen by the transmission electron microscope. Photon, a particle of light. Electromagnetic radiation. Electromagnetic radiation. So, that may be visible light, invisible light. So, all light, visible, invisible, comes under this electromagnetic radiation. and X-rays, gamma rays, radio waves, microwaves, ultraviolet rays, and infrared rays. Okay, like this. These are and so not on that one. See here, once you just check it off, this can be called as photon, a particle of light. What is photon? Photon is a particle of light. So this electromagnetic radiation is all kinds of light. All light, visible and invisible light, X-ray, gamma rays, radio waves, microwaves, ultraviolet rays, infrared rays, etc. comes under this category. Okay, now we can check it off here. See how the particles, photons of light transmission taking place. You can observe here. It's what interesting thing here we are observing here. That's what so how they are traveling, that is important in our discussion. So photon of particle of light in laser, from laser how this is looking like. You can observe the picture here. From laser here, this can be noticed like this. So, okay, once again I'll show you. This is how this movement is there for the particles, light particle, photon particle of light, how it travels. Like that earlier I've shown you. This is the picture, light particles movement. So it's a quite interesting thing here to learn about photons. It's a particle of light, right? So that is what electromagnetic radiation between highest energy to lowest energy is. A range here we have shown. This visible region, this gamma rays, X-rays, ultraviolet rays. Visible is a very small portion. You can observe here this ultraviolet radiation. Here that's of this is I'll show you here. This is visible region. This is visible region. So wavelength and nanometers we are taken here. This is observed the 400 to 750 nanometers wavelength region for the visible. You are only observing here the arrow marks. You can observe here only here. The lowest energy is 750 nanometers, and in the case of visible region, and 400 approximately 400 nanometers is the highest energy. This one is the visible region. So now you can observe here this all these things here we have visualized. And this, if you check it, a prism bends light, different colors are bent by different amounts. See, this is quite interesting and beautiful observation here. We are observing the prism bends light. There's a prism here. We are observing here. This is a prism here. This is, so white light is falling on this one. So once again, I'll show you. This is. So when it's falling on this one here, it moves like this here. A beautiful presentation here we have. That is from, it is spreading. Different colors are bent, but different amounts here like this. Different colors are coming from the prism. So once again, I'll show you. So prism bends light. That means different colors are bent by different atoms. So white light is passed into the prism. So it's moving like this here. Different colors like this. Next, so mass comparison. Proton is about 2000 times that of electron mass, and the electron is about, see, 1×10⁶ times a proton. It's not a proton, it's a photon. Proton, electron, photon. See, three things are there here: proton, electron, photon. See, photon is light energy, and proton is electrons coming from this category of subatomic particles. Now, photon is light energy. It's a matter. Do everything be made of matter? What are the building blocks of matter? So how many elements are there? So what this is opposite of mixture. Proton, neutron, electron. See, you can observe here proton, neutron, electron. Green, whatever the green coloration is here, we are observing here in this. That's what we are observing here, green coloration here. This we have quite interesting thing here. These electrons, which are okay, electrons are revolving here around a location. It's called its nucleus. Okay, this is one beautiful picture about the arrangement of atomic theories. Here, how the electron is revolving around it. And this red coloration sphere is nothing but a proton is taken, and blue coloration is taken as a neutron here. This is one of the interesting thing here. The electron shell, that is around this one only. This what is the green color is rotating? That is electron shell or electron cloud. We can call it as electron shell or electron cloud. And coming to that other thing here, once this is volume like this, this is nucleus influence will be there here, and that's what nucleus. Inside the nucleus we are observing this proton and electron. Proton and electron. This is a fundamental of an atom. Now, so what about this nucleus? Nucleus is the center of the atom, and it says protons and neutrons are there in this one. Electron shell, here you can again observe like this previous one is shown. And in this we have proton, neutron and electron. So the mass is here compared. Mass of proton is 1 Dalton, and that of neutron is 1 Dalton, and the electron is as approximation is all. This is a 0.0005. Charge +1 for proton, and neutron 0. Electron, it's -1. 1 Dalton is equals to 1 atomic mass unit. Proton, neutron, electrons. See, once you see the proton, neutron, electrons. In the case of s orbital, the 2 electrons maximum is required here in this case. There is existence for the s orbital. Okay. In this we have an interesting thing here, that is observing here. We have like this. We have a p orbital. If you observe here, s orbital, we observe like this. P orbital, how the electrons are revolving here. So 6 electrons are there around 1 in one orbital. How these 2 electrons, they are revolving here. We are observing here. That means this is occupation of 2 electrons in one orbital. That takes place for all the 3 kinds of orbitals. See, at a time, if the 6 electrons, if they're rotated in this way, in this manner, you can understand that this is one kind of interesting aspect of p orbitals picture. It's a 3-dimensional xyz axis. Along the xyz axis, this moment we can observe. It's a pictorial representation, quite interesting and nice representation here. Next, moving on to the d orbitals. Yeah, they are 5 order. We have dxz, dxy, dyz, dx square minus y square, and dz square here. They are 5 order. This first 3 are having the 4 lobes are there here. The blue coloration and orange coloration are shown here. This comes under this degenerate orbitals. In this first 3 comes under one set, and the next 2 comes under another set. We have, when it comes to the comparison between s orbital and p orbital, see here, s orbital here, electrons revolving like this, and p orbitals here, the first shell of the electrons. If you see the electronic configurations, in the first shell we have s orbital with 2 electrons revolve around the nucleus. We are observing here. Okay. Then after here, if you see the p orbital case here, this is what p orbital case here. This. Okay. And coming to the point here, that s orbital, there are 2 electrons here we are observing which are revolving, and in the case of p orbital, existence of 6 electrons are there here we are observing in the second orbit. In a case of third orbit, d orbitals also starts joining with s and p, right? This is regarding this one. And f orbitals, if you see f orbitals, 14 are there. The electrons existence, maximum existence of electrons in f orbitals is 14, and there are 10 electrons in d subshell, d orbital, 6 electrons in p orbital which are present. Okay, next we'll move to the next one, that is the element. What is element? Element is but atoms having a specific number of protons. It's called the elements made of atoms. Basic units of matter, nothing but atoms. Specific number of protons. We have different things are there. We are like, if you see the periodic table, a small presentation here in this: hydrogen, lithium, sodium, helium, neon, argon are present here. And in the case here, beryllium, boron, carbon, nitrogen, fluorine. Here, magnesium, aluminum, silicon. Like this, an interesting picture. So over 100 are the such type of elements are there we have. Now, let us come back to this discussion of electron shells. If you take the first shell, a subshell is present. While that of p subshell, in the first shell it's not possible. First orbit, a shell is nothing but orbit. When it comes to the second shell, there are 2 things can be existed. One is S subshell, another one is P subshell. While that of third shell, main principal level, if you check it in that, we'll have S subshell, P subshell. In addition to that one, we have D also possible, right? In the above picture, if you observe the neutrons and protons at nucleus will be concentrated, and around that electrons will revolve. Now let us see how the electron shells, once again the pictures, beautiful arrangements of electrons movements here shown. One is we have two electrons revolving here, two electrons, and 2s we have two electrons here is shown, and 2p, that's 6 electrons are revolving. This one, so 2p here shown, this arrow mark here, this is. While that of, if you see the 3s here, this is 3s. Yes. In a case of 3s here 3s or 1s, 2s, 3s all same, but in a case of p subshells, that they're quite different from that of that s. Okay, let's move to the next interesting thing here, that is in electron shells. Earlier what we have shown here, there are electronic shells are there. The shells, the general idea here shown. Remember this nucleus. Where is the nucleus is there? You can observe here. This is where the nucleus here. This is the location. It's called nucleus in the atomic structure, and the lot of s orbitals, 2s orbitals, big size here shown, big size. That imagination picture we have to see this. And while that the other lobes, if you observe, this comes under 2p orbitals cases, and this is the influence of the nucleus will be present up to here. This is this location. Next, atomic number. What is atomic number? The number of protons in an atom is called as atomic number. For example, if you see this hydrogen case here, this is one H1, this one electron is there around the nucleus, it is revolving. The positively charged species hydrogen here around that electron, how it's revolving, quite interestingly you can observe here. Right, let's move. Does it affect the atomic number, proton, atomic mass, atomic charge? See, protons, yes, neutrons, no, electrons, no. So atomic number affect only when proton number changes. Atomic mass affects, yes, atomic mass affects when protons and neutrons changed. But electrons number is changing means it won't get effects. Atomic charge will get affected when proton number changed. Neutron number change, also atomic charge number gets affected. Electron number changes, atomic charge definitely affects. So here if you observe, in the long form of periodic table we have quite interesting things here. If you see this one, if you cut it and join the other parts, then the small form of the table will come. But here if you see the scissor directions, the part of the elements separately will be studied for convenience. They are the block and F block elements, metals and transition elements, you can say D block and F block. They are quite interesting here. And in this study, if you see the blue coloration arrow mark, if you observe here, if you cut it off here, then you'll be seeing quite interestingly the other portion is nothing but P block. So here they are called P block elements. Show me the paper on that, you can check it off later. Happiness, unhappy, unstable, high energy. So in chemistry also for a particular element, we can give the information about instability. The atom is unstable because it's having high energy. If the atom is stable, it's having low energy. Okay. Happy means it is stable, unhappy means it is unstable. My fan club, see, atoms, it's rotating like this. This picture is interesting to understand how the construction of the subatomic particles are there in the atom. See, this is like this. How this is jumping tendencies. That means atom happiness will come. Electronic zero charge, because we have to balance the full shell peace orbital except helium. Yes, definitely these atoms are stable. So if you do it, definitely atoms will get stability. Hydrogen, see how the electrons are revolving in the observation. This is, if the neutrons or electrons, protons and neutrons are present in the nucleus, the electrons tries to come closer to the nucleus. Protons, because these are coming closer only because of protons, because protons are positively charged. If you see the lithium case, we have lithium. We have lithium is there, 3 electrons. Beryllium, we have in the case of beryllium with the 4 electrons are there. How the 4 electrons, see, stable, continuously they are evolving. In a case of boron, it will be looking like this, see, because we have 2 electrons are there in a piece of shell of boron, and 1 electron is there, shell of boron, that 1 electron is to top. The next, if you take the carbon case, it's quite interesting. Only there are 2 electrons in the piece of shell, they are revolving. In the case of carbon, it's quite difficult to observe also if they rotate like this. More than this speed they will rotate, but here if you see this one, you can understand how the picture is telling about the construction of the electrons inside the atom. So nitrogen, if you see, so there are 7 electrons, so they are revolving around the nucleus in shells. Is oxygen case. Oxygen is another picture we have. Okay, this is about oxygen case. Because once the number of protons and neutrons, protons number is increasing, obviously what will happen, there will be rapidity will increase, the speed of that electrons also closing to the proton, try to come closer and getting stability increases. In a case of halogen fluorine, these electrons revolve. In the case of neon, this is the picture. So all the electrons, outermost electrons are not going to take part in the revolution at a time. So depending on their inter-electronic forces, they'll try to rotate around the nucleus. Now we'll see the shells. Atom. Hydrogen case we have 1s1. Helium case we have 1s2. While that of lithium case, if you see, lithium. In the case of lithium, what happens? There are 3 electrons, so they are revolved around the nucleus. You can check it off. Right? And now we are observing the beryllium case. Beryllium. There are 4 electrons are there around this one. So 2 in 1s level and 2 in 2s level. Hydrogen a bit unstable, unhappy. Hydrogen is a bit unhappy. And helium very happy. See that emoji for helium. Okay. And that of file that of beryllium is not that much. This is not the is 50-50 is there. I will see the boron conditions. Yeah, they have 5 electrons adjusted in boron. See the picture now we are observing. That of nitrogen here is coming 7, carbon 6 is coming. All that of we have the different ideas are there here in this. If you observe here, how the 7 is coming, and that there are 3 unpaired electrons in the 3 unpaired electrons in the case of nitrogen case, that is giving stability according to this ideas. Now the point is very clear that oxygen we have only 2 electrons are there in the case of oxygen. And the 2p level unpaired electrons, but that if it is 3 it is stable, if it is completely filled also stable, but oxygen needs to reach the noble gas configuration, next noble gas configuration, by taking the electrons from the other atoms to undergo reactions. Okay, so now I'll see the fluorine case. So how the fluorine, yeah, there are 5 electrons are there in the case of fluorine. There are 5 electrons are there in the case of fluorine. And one is unpaired electron, one unpaired electron in the fluorine case we have. Okay, now coming to neon case, neon is happy. Neon is happy because it's completely filled configuration is there here. Neon is having completely filled electronic configuration. Yeah, let's have a discussion on this neon case here. That is, we have sodium. Let's move to the next one. That is sodium. We have one unpaired electron in the 3s level, which is unpaired electron is giving some unstability sodium. If it is not there, definitely this sodium will acquire the stability. So little unstable, reactive also, because of that one unpaired electron, sodium extensively shows its reactivity. Next one, you have magnesium case. If you observe magnesium, there are 2 electrons excess to that of neon, which is also so giving some instability as 2 electrons are excess. So it also tries to lose its electrons. Aluminium and silicon it continues the same scenario you can observe. Now we have hydrogen 1 electron, we have hydrogen 1 electron, like that. We have helium 2 electrons, a lithium that is of 1 unpaired electron, sodium 1 unpaired electron. You can observe those who are having 1 unpaired electron in the S subshell and the outermost shell, they all kept in one vertical line, right? That is nothing but a group. When you see the beryllium case here, beryllium case, and that of magnesium case, they comes under the second vertical line, that is second group. Boron and aluminum, the 3 outermost electrons are there, so they are present in the third vertical line, that third group. While that of carbon and silicon, this is present in the fourth vertical line, fourth group. These are nitrogen, phosphorus, oxygen, sulfur, so respectively fluorine, chlorine comes under halogens cases. While that of except helium, all the others, neon, argon, they're all having the 8 electrons in their around them in the nucleus. So these dots and all showing that number of electrons in the outer shell of the atoms. So valence electrons, these electrons we'll call it as valence electrons. So what are valence electrons? Valence electrons is the number of electrons present in the outside shell, right? So let's move the hydrogen case. Here hydrogen 1. That 1 is the number of protons, is the atomic number. That plus 1 is the charge of hydrogen. This 1.008 is the average atomic weight of hydrogen. That of this 2, if you observe here in this case, atomic number and charge, you identify that of 2 is exact atomic weight of this one. See, this is that of fluorine. If you observe here, that fluorine, and that fluorine, this 9 is atomic number, minus 1 is a charge. 18.998 is the average atomic weight of that one. That is about fluorine, right? That's not the other discussion. That is isotopes. Isotopes 1H1, 1H2, 1H3. See how this isotopes define the isotopes universe. Then you can write this one: the atoms of the same element, the same number of protons with a different number of neutrons. That is called isotopes. A set of atoms must be required here to understand this one. See here, we have 1H1, so 2H1, 1H2, 1H3 are there. See in this, the reddish colored one is nothing but this is a proton, right? This one, these two are there, right? If you observe this blue color and red color, you can understand the difference between this one. Earlier we are told that is a neutron and proton, which are located inside the nucleus. If you see 3 minus 1, that is 2, that is neutron number. Neutron is located in the nucleus with blue color, right? And reddish color one is proton. Now, quantum neutrons time. See, this is a calculation of neutron cases one. This is. Now we'll see the calculation of neutrons here. This 12 is the mass number. From that, if you subtract the proton number, you will get neutron numbers. So 6 is the number of neutrons in 12 carbon. And 13 carbon is there. In that we have 6 protons are there. So 13 minus 6 will come 7. 7 is the number of neutrons. Let us understand isotopes. So this carbon and 12, carbon 13 isotopes pictures with the electrons number. Here electrons in green locations, and that of protons in red locations, neutrons, these are in blue locations. Here see this interesting picture. Now we'll see this shells. So when it's coming farther and farther from that, then actually these names located are here. These are names of the atoms, elements here shown in this picture. So here in this picture, what we understand is dial atom here. These are nitrogen, carbon, so like that phosphorus, U, they're shown. This is, that means here in this neon is there, sodium is there, magnesium is there, aluminum, silicon, phosphorus, sulfur, chlorine, and a circle present. So like a picture on this is for a small game wise information. Now what are the rules? The rule in this discussion is nothing but 1s orbital fills first of the 2s of the 2p, next 3s, next 3p. Here capital S, actually that s orbital which holds only 2 electrons, that indicates the maximum existence of s orbital is 2. What is the maximum existence of p orbital is 6. It is having the 3 subshells. First orbital, second orbital, third orbital. There's an idea here shown. And now noble inert gas elements. And this we have helium, neon, argon, krypton, xenon, radon. So p shell is completely filled in this case, except helium. Helium is not having p because atomic number is very small in this case. And they have very non-reactive cases that they're very happy because they are quite stable. And next, coming to the other thing here, this other part of this one, these are the metals here. These are the metals. Here, this location here, we are observing here. These are the metals. Coinage metals also included. Their extra electrons are there compared to the noble gases. They are conductive and they are malleable. That means we can make them whites and all these things. And dense, they are shiny as well as they are ductile. This is quite interesting thing regarding metals. Here we have all these locations: hydrogen, lithium, sodium, potassium, beryllium, magnesium, calcium. Even particularly we have D block elements. They have such type of tendency of exhibiting high densities and all these things. Next. Metal, an atom with 1 to 3 extra valence electrons usually shines dense, malleable, ductile, electrical conductors, and they are thermal conductors also. See, these are the tendency of such kind of metals is shining property, density property. So they have density also will be there. Malleable means we can make them whites and sheets. Electrical conductors, thermal conductors. And in the case of potassium, sodium, see, we list given in the extreme left side of this table. The reactivity decreases from top to bottom. That's the meaning of it. And when you see from right to left in the periodic table, reactivity increases from top to bottom in the periodic table. In a group, the reactivity increases. Right? So now this one in this can understand one thing, that the metals are reactive, and that reactive metals are located on the left side of the periodic table. And in a group, why this reactivity is shown like this is metals are said to be coming on the bottom side of every group. Let us see the individual metal atoms with the free outer shell electrons. These are all individual metal atoms with the free outer shell electrons. So free electrons are moving around that atoms here. This green coloration here showing they are nothing but individual metal atoms with the free outer shell electrons. So in this juncture we can understand one important word, that is metallic bond. That means a sharing of valence electrons by neighboring metal atoms causes this peculiar chemical bond called as metallic bond. Right? Let us see. Electricity. How electricity can be understood in the atom theories. These electrons are moving through a metal wire usually. So then that movement of electrons, we'll call it as electricity. So that is regarding metals. So regarding metals we saw these different ideas. Now regarding non-metals we will see, that is non-metals actually they're having some missing electrons. If they have electrons, definitely they will get unhappiness, like noble gases. They're non-conductive because they don't have any extra electrons, because extra electrons are actually responsible for non-conductivity and are not malleable. Non-metals are not malleable and they are dull in nature. And come to the other, we have metalloids are there, they are partly conductive and they are boron, silicon, germanium, arsenic, antimony, tellurium, polonium. These are the best examples of its kind. This is regarding atomic structure, what we have discussed in this session. Okay. So this is what an interesting topic today we have taken. This is for basic information for all the students, which is required in this atomic theories. Okay. So here we have started this the part we have discussed today for all the students from 8th standard to +1 level. Okay. Thank you very much for this session. Hope you got some good presentations in this class.